Detailed introduction of vacuum hot press sintering furnace. The vacuum hot pressing sintering furnace is an advanced material processing equipment primarily used for sintering and shaping powder materials through a combination of high temperature heating and mechanical pressing under vacuum or protective atmosphere conditions. It integrates vacuum environment, hot pressing molding, and high-density sintering functions into one, and is widely used in powder metallurgy, ceramics, composite materials, and other fields, helping to prepare high-density material products. Shanghai Haoyu is a professional vacuum furnace manufacturer, and the vacuum hot pressing furnace is one of its most mature and popular products, suitable for scientific research institutions, universities, and industrial production. One working principle. The working process of a vacuum hot press sintering furnace typically involves several steps. First, evacuation is performed to create a low pressure or oxygen-free environment. Then, the material is heated to high temperatures, typically up to 2,000–2,400 degrees Celsius, by heating elements. Finally, uniaxial or biaxial pressure is applied via a hydraulic system to promote interparticle bonding, grain growth, and eliminate voids, pores, and defects. The vacuum environment effectively prevents the material from undergoing oxidation or contamination reactions with oxygen, water vapor, etc. in the air at high temperatures, thereby improving the purity and performance of the material. Specifically, materials such as metal powder, ceramic powder, or nanomaterials are placed in a mold and heated to a temperature close to their melting point under vacuum conditions, while pressure, typically ranging from several tons to tens of tons, is applied. The pressure aids in particle rearrangement and plastic deformation, accelerating the diffusion and densification processes, ultimately resulting in the formation of a high-density, uniform solid material. This hot press sintering is more efficient than traditional sintering, significantly reducing processing time and improving the mechanical properties of the material. 2. Structural composition. The vacuum hot press sintering furnace boasts a compact structural design and comprehensive functionality, primarily comprising the following components. Furnace body and vacuum system. The furnace body is typically a vertical or horizontal structure, featuring a double-layer water-cooled wall design to withstand high temperatures and pressures. The vacuum system comprises a vacuum pump set, such as a mechanical pump, diffusion pump, or molecular pump, capable of achieving high vacuum levels, with an ultimate vacuum degree of up to 10 4 PA or higher, ensuring a pollution-free environment. Heating system. Common heating methods include resistance heating, induction heating, or microwave heating. Heating elements such as graphite heating bodies can rapidly heat up and distribute the heat field evenly, with a maximum temperature of up to 2,400 degrees. Pressurization system consists of a press head, single press head, or upper and lower dual press heads, driven by a hydraulic press and an oil cylinder, providing precise pressure control ranging from several tons to hundreds of tons. The press head is typically made of high-temperature resistant materials such as graphite or tungsten alloy. Cooling system, water-cooled or air-cooled system, used for rapid cooling to prevent material deformation due to overheating. Some equipment is also equipped with an inert gas filling function to achieve protective atmosphere sintering. Control and monitoring system, including temperature controller, pressure sensor, vacuum gauge, and temperature measuring instruments, such as thermocouple or infrared thermometer. The equipment integrates PLC and touchscreen control or industrial computer to achieve automated operation and data reporting. Auxiliary components such as molds, heat shields, reflective screens, and safety valves ensure stable operation of the equipment. The equipment specifications vary depending on the model. For example, the P5V series furnace body can be designed in different sizes, suitable for laboratory or industrial scale. 3 advantages. Compared to traditional sintering furnaces, vacuum hot press sintering furnaces possess the following notable advantages. High density. Through pressure assistance, materials with near theoretical density up to 99% or more can be obtained, reducing pores and defects and improving mechanical strength and durability. Oxidation prevention and purification. A vacuum environment prevents material contamination, making it suitable for easily oxidizable or refractory metals such as tungsten and molybdenum. High efficiency and energy saving. Heating and pressurizing are carried out simultaneously, shortening the sintering time and reducing energy consumption. Versatility. Capable of processing various materials, including metal compounds, ceramics, inorganic nonmetals, nanomaterials, etc., and also supports diffusion welding. Precise control. Temperature, pressure, and vacuum degree can be finely adjusted, making it suitable for scientific research experiments and small-scale production. For application areas, vacuum hot press sintering furnaces are widely used in multiple high-tech fields: powder metallurgy, preparation of high-performance alloys, cemented carbide tools, and wear-resistant components. Ceramic materials produce transparent ceramics, industrial ceramics, such as zirconia and alumina, and functional ceramics for electronic components and medical devices. Aerospace, high-temperature pressure diffusion welding for processing rare metals and precious materials, such as titanium alloys or high-temperature ceramic composites. Photovoltaic and nanomaterials, sintering photovoltaic materials, such as lanthanum hexaboride and nanometer powders for use in semiconductors, batteries, and sensors. Others, used for preparing high-density, high-temperature resistant products in the fields of biomaterials, automotive parts, and national defense. 5 precautions and technical parameters. When using, it is important to pay attention to safe operations, such as avoiding sudden leakage under high pressure and regularly maintaining the vacuum pump and heating elements. And of the vacuum hot press sintering process of boron carbide powder. This video will start with the preparation work and show step by step how to use a vacuum hot press furnace to complete the sintering process. Boron carbide is a high hardness ceramic material commonly used in bulletproof and wear-resistant applications. Please note that all operations should be carried out in a professional laboratory environment and strictly follow safety regulations. The operator checks the sealing of the vacuum hot pressing furnace, the operation of the vacuum pump, the heating elements, and the pressure system. Boron carbide powder particle size is less than or equal to strontium purity, 99%. Is weighed using a balance. If additives, such as a small amount of carbon powder, are required, they are mixed evenly here. Close-up of the mold assembly process from an empty mold to being filled with powder. Action description. Clean the graphite mold and apply release agent. Fill the weighed boron carbide powder evenly into the mold and use a vibrating table or manual compaction for preliminary molding. Assemble the mold upper cover, ensuring alignment. Next comes the loading process. Fill the graphite mold with boron carbide powder. The mold needs to be cleaned in advance and coated with a release agent to prevent sticking. Distribute the powder evenly and perform preliminary compaction to ensure uniform sintering. This step directly affects the density and performance of the final product. Placing into the furnace and vacuumizing, carefully place the assembled mold into the chamber of the vacuum hot pressing furnace. Close the furnace door and start the vacuum pump to evacuate the chamber to approximately 10.3 Pa. Monitor the vacuum gauge. Place the mold into the vacuum hot pressing furnace. After closing the furnace door, activate the vacuum system to gradually remove the air and moisture inside the furnace chamber until a high vacuum state, usually below 10.3 Pa, is achieved. The vacuum environment prevents oxidation and impurity contamination, ensuring sintering quality. Heating and pressurization process. Initiate the heating program and increase the temperature at a rate of 10-20 degrees Celsius, min to the target temperature 1850-1950 degrees Celsius. When a temperature reaches approximately 1000 degrees Celsius, begin applying pressure 30-40 MPa and maintain it at a peak temperature for 1-2 hours. Monitor the temperature and pressure curves. Entering the core sintering stage, the furnace heats at a controlled rate while applying axial pressure at an appropriate temperature. This promotes diffusion and bonding between powder particles, achieving densification. Typical parameters are temperature of 1850-1950 degrees Celsius, pressure of 30-40 MPa, and holding time of 1 hour. The entire process is carried out under vacuum to suppress bubble formation. Cooling and stress relief. Action description. After heat preservation is completed, gradually release the pressure and cool down to room temperature at a rate of 5-10 degrees Celsius min. During the cooling process, maintain vacuum or introduce an inert gas, such as argon, to prevent oxidation. After sintering is completed, cooling begins. The temperature and pressure are gradually reduced to avoid cracks caused by thermal stress. After cooling to room temperature, the remaining vacuum is released and the sample is ready to be removed. This step usually takes several hours to ensure the integrity of the material. Sample retrieval and post-processing. Open the furnace door and remove the mold. Carefully demold to obtain the sintered boron carbide block. Clean the surface and inspect the density, hardness, and microstructure using a microscope or densitometer. If necessary, perform machining or testing. Finally, remove the sintered product. Disengage the boron carbide ceramic block from the mold, clean its surface, and conduct quality inspection. The ideal product should have a density close to the theoretical value, 99%, high hardness, and no obvious defects. At this point, the entire vacuum hot press sintering process is complete. Thank you for watching. Through vacuum hot press sintering, we have obtained high-performance boron carbide ceramics. In practical operations, please consult professional guidance and pay attention to safety. For more content on material science, stay tuned.